Long before the age of unified science, the human understanding of nature was fragmented, cautious, and incomplete. The world was interpreted through separate lenses, each one describing a different mystery. Light dazzled the eye but remained elusive in its true nature. Electricity shocked and sparked, a force of sudden violence and curiosity. Magnetism pulled invisibly, quietly commanding iron and compass needles. These phenomena were observed, catalogued, and even used in limited ways, yet they lived in separate intellectual compartments. Scientists treated them as unrelated actors on the stage of nature, each obeying its own rules, each demanding its own explanations. The idea that they might be deeply connected seemed unnecessary, even absurd, because no obvious bridge existed between them. For centuries, light had been associated with vision, astronomy, and optics. Ancient thinkers debated whether light was made of particles or waves, whether it traveled instantly or at a finite speed. Lenses and mirrors were studied to improve telescopes and microscopes, but light itself was rarely thought of as a physical force. It was something that illuminated objects, not something that acted upon them in a mechanical way. Even when Isaac Newton explored optics, his focus was on refraction, color, and geometry, not on any connection to electricity or magnetism. Light belonged to the realm of sight, not force. Electricity followed a very different path. Early experiments involved static charges, sparks from rubbed amber, Leyden jars, and dramatic shocks. Electricity felt alive and dangerous, capable of producing sudden motion and heat. Yet it seemed unpredictable and poorly behaved. It was studied in laboratories as a curiosity, more spectacle than theory. Scientists could generate it, store it briefly, and release it, but they did not fully understand what it was or how it moved. There was no clear sense of electricity as a continuous phenomenon spreading through space. It appeared local, momentary, and confined. Magnetism, meanwhile, carried an ancient mystique. Lotus stones had been known since antiquity, guiding sailors across oceans with invisible authority. Magnetic forces acted silently, without sparks or light, reaching across space without contact. This made magnetism feel mysterious and almost supernatural, yet it seemed stable and dependable, unlike the volatile nature of electricity. For a long time, magnetism was treated as a property of certain materials, rather than a fundamental force of nature. The first cracks in this separation began to appear in the early 19th century. Experiments showed that electricity and magnetism were not entirely independent. Electric currents could deflect magnetic needles. Changing magnetic fields could induce electric currents. These discoveries hinted at a relationship, but the connection was incomplete and confusing. Scientists could observe interactions, but they lacked a unifying explanation. The laws describing electricity were mathematical recipes derived from experiments. The laws of magnetism were similar collections of rules. They worked, but they did not explain why they worked or how they fit together. This fragmented view of nature reflected a deeper limitation in scientific thinking at the time. Forces were imagined as acting directly between objects, often instantaneously. Space itself was treated as empty and passive, merely the distance separating causes and effects. If something happened, it was because one object acted on another across space. The idea that space itself could play an active role in transmitting forces was not yet fully accepted. This mental framework made it difficult to see connections between phenomena that did not obviously interact. Into this world of separation and incomplete understanding, James Clerk Maxwell was born. He did not inherit a unified science, he inherited a collection of puzzles. From an early age, Maxwell showed a remarkable ability to see patterns where others saw chaos. He was not satisfied with surface descriptions. He wanted to understand the hidden structures that governed how nature behaved. This mindset was crucial because the unification of light, electricity, and magnetism required more than new experiments. It required a new way of thinking. Before Maxwell, Michael Faraday had introduced a revolutionary concept: fields. Faraday imagined electric and magnetic forces not as invisible strings pulling objects together, but as conditions existing throughout space. Lines of force filled the space around charges and magnets, curving, stretching, and interacting. Faraday's ideas were visual and intuitive, but he lacked the mathematical tools to express them precisely. Many scientists admired his experiments, but dismissed his field concept as too vague. Maxwell saw something profound in Faraday's vision. He realized that fields could provide the missing link between electricity, magnetism, and light. Instead of treating forces as separate actions, Maxwell began to think of them as manifestations of underlying fields that could change, move, and interact. This shift in perspective was revolutionary. It transformed space from a passive background into an active participant in physical processes. At the time, this way of thinking was deeply unconventional. Most physicists preferred equations that described direct interactions between measurable quantities. Maxwell, however, was willing to trust abstract reasoning if it led to deeper understanding. He believed that mathematical structures could reveal truths about nature, even before experiments confirmed them. This belief placed him ahead of his era. The world before Maxwell's unification was one where technology advanced slowly and unevenly. Practical applications existed, but they were limited by incomplete theory. Engineers worked by trial and error, guided by experience rather than deep understanding. Without a unified framework, it was difficult to predict new phenomena or design systems that exploited unseen connections. The potential locked inside electricity and magnetism remained largely untapped. Light, too, was constrained by limited theory. Its wave nature was debated, but the medium through which it traveled remained hypothetical. The concept of an ether filled scientific discussions, an invisible substance thought necessary to carry light waves through space. This ether complicated theories and raised questions that could not be answered. Why did Earth's motion not affect the speed of light? Why could the ether not be detected? These problems lingered unresolved. The separation of forces also influenced how scientists viewed the universe as a whole. Nature appeared messy, governed by different rules in different domains. There was no sense of deep unity, no underlying simplicity. Each discovery added complexity rather than coherence. This worldview limited imagination. If light, electricity, and magnetism were unrelated, then no single theory could explain them together. Science progressed, but without harmony. Maxwell's genius lay in recognizing that this fragmentation was not a reflection of nature itself, but of human understanding. He suspected that the universe was more unified than it appeared, and that the apparent separation of phenomena was an illusion created by incomplete models. This conviction drove him to search for connections where others saw boundaries. In the pre-Maxwell world, the idea that light could be an electromagnetic phenomenon would have seemed implausible. Light did not produce sparks or move needles. Electricity did not illuminate the sky in gentle waves. Magnetism did not warm objects or produce colors. The sensory experiences associated with each phenomenon were too different. Yet Maxwell understood that nature does not care about human perception. What matters are the underlying processes, not how they appear to our senses. This insight required intellectual courage. To connect light with electricity and magnetism, Maxwell had to challenge deeply held assumptions. He had to accept that forces could propagate through empty space without a material medium. He had to imagine fields oscillating, feeding into each other, creating self-sustaining waves. None of this was directly observable at the time. It existed only in mathematics and imagination. The first keynote, The World Before Unity, is therefore not just a historical background. It represents a fundamental stage in human thought, when knowledge grows but remains compartmentalized. It shows how progress can be limited not by lack of data, but by lack of perspective. Before Maxwell, scientists had many pieces of the puzzle, but no picture on the box to guide them. This fragmented understanding also shaped how society perceived science. Discoveries were impressive but isolated. There was no sense that a single idea could transform multiple fields at once. The power of unification, the ability of one theory to explain many phenomena, had not yet revealed itself fully. Maxwell's work would change that forever, but only because it emerged from a world that desperately needed connection. Understanding this unified world allows us to appreciate the magnitude of Maxwell's achievement. He did not merely add a new theory to an existing collection. He reorganized the entire structure of physical understanding. He showed that what appeared separate was actually connected, and that the universe operated according to deeper principles than previously imagined. In this earlier era, nature whispered clues, but no one could yet hear the full message. Sparks leapt, needles turned, light traveled across the cosmos, all obeying rules that were related but not yet revealed. The stage was set for a mind capable of seeing beyond categories, beyond experiments, beyond tradition. The world before unity was not ignorant, but incomplete, and it was precisely this incompleteness that made Maxwell's insight not only possible, but necessary. As the 19th century progressed, the scientific world became increasingly crowded with facts, but increasingly poor in meaning. Laboratories across Europe were producing results at an unprecedented rate. New instruments measured currents, voltages, magnetic strengths, and optical effects with growing precision. Yet this abundance of data did not bring clarity. Instead, it deepened the sense that nature was a patchwork of rules rather than a coherent system. Scientists knew more than ever, but understood less than they hoped. Each phenomenon seemed to demand its own explanation, its own theory, its own language. This situation created a subtle tension within science. On the surface, progress appeared strong. Telegraph wires were spreading across continents. Electric motors were being explored. Optical instruments were improving astronomy and medicine. But beneath these advances lay a fragile foundation. Engineers could build devices that worked, but often could not explain why they worked beyond narrow circumstances. When conditions changed, predictions failed. Without a unifying theory, science advanced horizontally, not vertically. It expanded outward without digging deeper. One of the greatest obstacles to unity was the concept of action at a distance. Forces were assumed to act instantly across space, without delay and without a medium. Gravity, electricity, and magnetism were all treated this way. While mathematically convenient, this idea felt philosophically troubling to many thinkers. How could an object here influence another object far away without anything in between? The discomfort was often ignored because there was no alternative framework capable of replacing it. Faraday's field concept challenged this assumption, but it remained controversial. To many mathematicians, Faraday's lines of force looked like drawings rather than rigorous science. They lacked equations, symbols, and predictive power. As a result, Faraday's deepest insight, that space itself could store and transmit energy, was admired but not fully embraced. The scientific community stood at a crossroads, unsure whether to remain loyal to familiar methods or risk adopting a radically new way of thinking. Light added another layer of confusion. If light was a wave, it seemed to require a medium, just as sound requires air or water waves require liquid. This hypothetical medium, the luminiferous ether, became one of the most debated ideas in physics. It was imagined as filling all space, incredibly rigid to allow fast wave motion, yet offering no resistance to moving planets. The ether was invisible, undetectable, and increasingly paradoxical. Still, it was widely accepted because no better explanation existed. Electricity and magnetism did not seem to require such a medium. Their effects appeared tied to charges and currents rather than waves traveling freely through space. This difference reinforced the belief that light belonged to a separate category of phenomena. Even when experiments hinted at wave-like behavior in electrical systems, the implications were not fully explored. The mental barriers between disciplines were strong. Education reflected this fragmentation. Students learned optics in one course, electricity in another, magnetism in another still. Textbooks treated them as distinct subjects with minimal overlap. This separation shaped how new generations of scientists thought about nature. They were trained to specialize, not to synthesize. While specialization brought precision, it also narrowed vision. Maxwell entered this intellectual landscape with an unusual balance of imagination and discipline. He respected experimental results, but he was not enslaved by them. He believed that theory should not merely summarize known facts, but reveal hidden relationships. This belief allowed him to look at the cluttered landscape of 19th-century physics and suspect that its apparent complexity masked an underlying simplicity. The world before unity was therefore not merely a stage of ignorance. It was a necessary stage of accumulation. Nature had to be explored in pieces before it could be understood as a whole. Electricity had to be isolated, magnetism had to be measured, light had to be analyzed. Only when enough pieces were available could someone attempt to see the full picture. Maxwell's achievement depended on the work of countless others, even though they themselves did not see where their discoveries were leading. There was also a psychological dimension to this fragmented world. Scientists became cautious. Proposing grand unifying theories carried risks. If a theory failed, it could damage reputations built on careful, incremental work. As a result, many preferred to focus on narrow problems with clear experimental support. Maxwell, however, was willing to risk misunderstanding. He was comfortable working in abstraction, trusting that clarity would eventually emerge. In this sense, the world before unity was as much about mindset as knowledge. It was a world that valued certainty over coherence, measurement over meaning. Maxwell challenged this balance. He showed that true understanding sometimes requires stepping beyond what is immediately observable. His willingness to do so was not reckless, it was guided by mathematical consistency and physical intuition. The lack of unity also affected how time and causality were understood. If forces acted instantly, there was no need to consider delays or propagation speeds. This assumption simplified equations but hid deeper truths. Maxwell's later realization that changes in electric and magnetic fields propagate at a finite speed would overturn this assumption completely. But before that could happen, science had to recognize the limitations of instantaneous action. From a modern perspective, it is tempting to view the pre-unified world as primitive. This would be a mistake. It was a world of brilliant minds, careful experiments, and genuine progress. Its limitation was not intelligence but perspective. The tools for unification existed, but they had not yet been combined in the right way. Maxwell did not create unity from nothing. He revealed it by rearranging what was already known. This period also illustrates an important truth about scientific revolutions. They do not arise simply because new facts are discovered. They arise when someone sees existing facts differently. Maxwell's genius was not in discovering new electrical laws or inventing new instruments, but in recognizing that familiar laws could be interpreted as parts of a single system. His work reminds us that progress often depends on interpretation as much as observation. The world before unity was therefore a world waiting for connection. It was rich in phenomena, but poor in synthesis. Light crossed space from distant stars. Electric currents flowed through wires. Magnetic fields guided navigation. Each operated according to rules that were known but isolated. The connections between them lay hidden, not because nature concealed them, but because human thought had not yet learned how to look. When Maxwell eventually unified these forces, the transformation would be so complete that it would become difficult to imagine how science ever functioned without that unity. But understanding the pre-Maxwell world allows us to appreciate how radical his vision truly was. He did not simply solve a problem, he changed the way problems were defined. The first keynote, then, is a story of separation that sets the stage for connection. It shows a scientific world full of brilliance, yet divided by conceptual walls. It reveals the limits of observation without synthesis, of knowledge without integration. And it reminds us that the greatest breakthroughs often come not from discovering something entirely new, but from realizing that what we already know is more deeply connected than we ever suspected. In that world before unity, nature was speaking in fragments. Sparks spoke one language, magnets another, light another still. Maxwell would eventually listen to all of them at once and recognize that they were telling the same story. But before that story could be told, science had to reach the point where fragmentation itself became a problem in need of a solution. That moment arrived quietly, without fanfare, in the mind of a man who believed that the universe, at its deepest level, must make sense. From the outside, James Clerk Maxwell did not look like a revolutionary. He was not loud, not theatrical, and not driven by the desire to shock the world. His appearance was modest, his behavior gentle, and his personality reflective. Yet behind this quiet exterior was a mind unlike any other of his time, a mind capable of seeing connections where others saw only separation. The second keynote, the mind that saw invisible connections, is not about a single discovery, but about a way of thinking that transformed science at its roots. Maxwell's genius lay in his ability to move effortlessly between imagination and rigor. Where some scientists relied almost entirely on experiment, and others relied solely on mathematics, Maxwell combined both into a single intellectual vision. He could visualize physical processes in space, imagine how invisible forces might behave, and then translate those images into precise mathematical language. This rare balance allowed him to explore ideas that seemed unreachable to others. From his earliest years, Maxwell showed an unusual sensitivity to patterns. As a child, he was fascinated by shapes, curves, and symmetry. He asked questions that went beyond surface appearances. He wanted to know why bubbles form perfect spheres, why reflections behave predictably, why motion follows hidden rules. This habit of seeking underlying structure became the foundation of his later work. He did not accept phenomena as isolated facts. He assumed they were expressions of deeper principles. When Maxwell encountered the existing theories of electricity and magnetism, he immediately sensed that something was missing. The equations worked, the experiments were reliable, but the overall picture felt incomplete. There was no unifying story, no conceptual framework that explained how these forces truly operated in space and time. Many scientists were comfortable with this situation. Maxwell was not. His mind resisted fragmentation. He believed that nature must be internally consistent and that apparent complexity often hides a simpler truth. One of Maxwell's most remarkable traits was his ability to take ideas seriously even when they were unpopular or poorly understood. Michael Faraday's concept of fields is a perfect example. Faraday imagined electric and magnetic effects as lines of force filling space, bending and interacting like elastic threads. To many mathematicians, this seemed unscientific, even childish. But Maxwell saw past the lack of formalism and recognized the deep physical insight behind Faraday's intuition. Maxwell did something extraordinary. He treated Faraday's visual ideas as clues rather than flaws. Instead of dismissing them, he asked how they could be expressed mathematically. He asked what kind of equations would describe a space filled with forces rather than objects acting at a distance. This shift required imagination of a very high order. Maxwell had to picture space not as emptiness, but as an active environment capable of storing energy and transmitting change. To think this way required abandoning comfortable assumptions. Action at a distance had dominated physics for centuries. It allowed forces to act instantly, without explanation. Maxwell questioned this deeply. He felt that instant action was not a true explanation, but a placeholder for ignorance. His mind searched for a mechanism, a process by which forces could move and evolve. Fields provided that mechanism. What made Maxwell's thinking truly exceptional was his willingness to trust abstract reasoning. He did not demand immediate experimental proof for every idea. Instead, he looked for internal consistency, symmetry, and mathematical beauty. If an idea fit logically with known laws and extended them naturally, he considered it worth pursuing. This approach allowed him to venture far beyond the experimental limits of his time. Maxwell's notebooks reveal a mind constantly exploring, revising, and refining ideas. He experimented with mechanical models of fields, imagining gears, vortices, and elastic media filling space. These models were not meant to be literal descriptions of reality, but tools to guide intuition. They helped him understand how energy might flow through space and how changes in one place could influence another. Once the intuition was clear, he translated it into equations and discarded the mechanical imagery. This ability to move between metaphor and mathematics was central to Maxwell's success. Many scientists could do one or the other. Few could do both at such a high level. Maxwell's metaphors were not random. They were carefully chosen to capture essential features of physical behavior. His mathematics was not cold abstraction. It was deeply connected to physical meaning. Another aspect of Maxwell's mind was his comfort with invisibility. He was not troubled by the fact that fields could not be directly seen. He understood that science often deals with entities that are inferred rather than observed. Atoms, forces, and waves all belong to this category. What mattered was not visibility but explanatory power. If an invisible concept made sense of many phenomena at once, it deserved serious consideration. This attitude allowed Maxwell to imagine electric and magnetic fields changing in time, interacting with each other, and propagating through space. He was able to think dynamically, not statically. Where earlier theories focused on steady states and equilibrium, Maxwell embraced change and motion. He asked what happens when fields evolve, when currents start and stop, when forces fluctuate. This focus on dynamics was crucial for revealing the wave-like nature of electromagnetic phenomena. Maxwell also possessed an extraordinary ability to hold multiple ideas in his mind simultaneously. He could consider electricity, magnetism, optics, and mechanics as parts of a single system. This mental integration was rare in an age of increasing specialization. While others focused narrowly on their own fields, Maxwell moved freely between disciplines, borrowing concepts and methods wherever they proved useful. His education played a role in shaping this versatility. Maxwell was deeply trained in mathematics, but he was also interested in philosophy, poetry, and art. He did not see science as isolated from culture or human creativity. This broader intellectual background enriched his scientific thinking. It allowed him to approach problems from unconventional angles and to value elegance and simplicity alongside accuracy. Despite his brilliance, Maxwell was not arrogant. He was acutely aware of the limits of his knowledge and the provisional nature of theories. This humility made him open to revision and refinement. When his ideas evolved, he adapted them without attachment to earlier formulations. His goal was understanding, not personal validation. The mind that saw invisible connections was therefore not driven by ego or ambition, but by curiosity and coherence. Maxwell wanted the world to make sense. He believed that beneath the apparent complexity of phenomena lay a deeper order waiting to be discovered. This belief guided his work even when recognition was slow or absent. In practical terms, Maxwell's thinking transformed scattered experimental laws into a unified theoretical structure. But at a deeper level, it transformed the philosophy of physics. It showed that unseen entities like fields could be just as real as tangible objects. It demonstrated that mathematics could reveal truths beyond immediate observation. And it proved that unification is not merely a convenience, but a powerful path to deeper understanding. Maxwell's way of thinking also changed how future scientists approached problems. It encouraged them to look for connections across domains, to value theoretical insight alongside experiment, and to trust the power of abstraction. Without this intellectual shift, later revolutions in physics would have been impossible. The second keynote is ultimately about vision. Not vision of the eyes, but vision of the mind. Maxwell saw relationships that others could not yet imagine. He listened to different phenomena and heard harmony where others heard noise. His mind functioned like a bridge, connecting islands of knowledge into a single continent. This capacity did not arise by accident. It was cultivated through patience, curiosity, and a willingness to question assumptions. Maxwell's genius reminds us that scientific breakthroughs are not only about intelligence, but about perspective. To see invisible connections, one must be willing to look beyond familiar categories and trust that nature is more unified than it appears. In Maxwell's hands, electricity and magnetism ceased to be separate curiosities. They became expressions of a deeper reality. And light, once thought unrelated, would soon be drawn into this same framework. All of this began not with a dramatic experiment, but with a mind capable of seeing what others overlooked. The story of Maxwell's mind is therefore a story of intellectual courage. It is the courage to imagine that the world is simpler than it seems, to believe that unity exists even when evidence is fragmented, and to pursue that unity with patience and rigor. This mindset did not just change one field of science. It changed the way humanity understands the universe itself. As Maxwell's thinking matured, his ability to see invisible connections became even more refined. He did not rush toward conclusions. Instead, he allowed ideas to develop slowly, testing them against known facts and internal logic. This patience was crucial, because the connections he was uncovering were not obvious. They did not announce themselves through dramatic experiments or sudden observations. They revealed themselves only through sustained contemplation and careful synthesis. One of the most remarkable features of Maxwell's mind was his sensitivity to inconsistency. When two laws described related phenomena but used different assumptions or structures, Maxwell felt uneasy. To him, inconsistency was a signal that understanding was incomplete. This discomfort drove him to search for deeper explanations that could reconcile apparent contradictions. Where others accepted imperfect matches between theory and reality, Maxwell saw an invitation to think further. His treatment of electricity and magnetism illustrates this perfectly. Experimental laws described how charges and currents behaved, but they did not fully explain how changes propagated through space. Maxwell asked questions that few others thought to ask. What happens in the space between a charge and another charge? What changes when a current starts flowing? How does the influence of one region reach another? These questions forced him to think beyond objects and focus on processes. Maxwell's imagination was not free, floating fantasy. It was disciplined imagination, constrained by mathematics and physical intuition. He often constructed mental pictures of how fields might behave, how they might stretch, rotate, or interact. These pictures helped him grasp complex relationships that could not be easily expressed in words. Once he understood the behavior intuitively, he translated it into equations that captured the essence without the imagery. This approach allowed Maxwell to unify ideas that seemed fundamentally different. Electricity involved charges and currents. Magnetism involved fields and forces on moving charges. Light involved waves and oscillations. Maxwell's insight was to recognize that these differences were superficial. At a deeper level, all three involved variations in fields that could influence each other over space and time. Seeing this required a mental flexibility that few possessed. Maxwell was also unusually comfortable with abstraction. Many scientists of his time distrusted abstract entities that could not be directly measured. Maxwell, however, understood that abstraction is a tool, not a flaw. He knew that atoms, fields, and waves were all theoretical constructs designed to explain observations. Their value lay in how well they organized knowledge and predicted new phenomena, not in their immediate visibility. This philosophical openness allowed Maxwell to push beyond the limits of existing experimental techniques. He accepted that some aspects of reality might remain unobservable for a time. Rather than waiting for instruments to catch up, he allowed theory to lead. This was a bold stance, but it was grounded in careful reasoning. Maxwell did not invent concepts arbitrarily. He introduced them because they solved real problems and brought coherence to scattered laws. Another defining aspect of Maxwell's mind was his appreciation for symmetry. He believed that nature favored balanced, elegant structures. When equations displayed symmetry, he took it as a sign that they reflected something fundamental. When they appeared awkward or asymmetrical, he suspected that something was missing. This aesthetic sense guided his work just as much as empirical data. Symmetry helped Maxwell recognize that electric and magnetic phenomena were not merely related, but intertwined. Changes in one could generate changes in the other. This mutual dependence suggested a deeper unity, one that could support self-sustaining processes. The idea that electric and magnetic fields could feed into each other dynamically was revolutionary, but it fit naturally with Maxwell's sense of balance and reciprocity. Maxwell's thinking also benefited from his emotional detachment from immediate success. He was not driven by the desire for recognition or quick validation. This allowed him to pursue ideas that seemed obscure or unappreciated. When his work was misunderstood or ignored, he did not abandon it. He trusted that clarity would emerge with time. This patience proved essential because the implications of his ideas were not immediately obvious even to himself. When Maxwell first unified electricity and magnetism mathematically, he did not fully grasp how transformative the result would be. He followed the logic where it led, without anticipating its ultimate consequences. This humility kept his focus on understanding rather than impact. Maxwell's personal temperament also played a role. He was introspective and reflective, comfortable spending long periods in thought. He did not need constant external stimulation. This inner focus allowed him to explore complex conceptual landscapes without distraction. His notebooks reveal a mind engaged in continuous dialogue with itself, questioning, refining, and deepening its ideas. The scientific culture of the time often rewarded specialization and productivity. Maxwell moved against this trend. He valued depth over volume. He published relatively little compared to some of his contemporaries, but what he published was dense with insight. Each contribution represented years of thought and synthesis. His mind worked like a slow but powerful engine, building understanding layer by layer. The invisible connections, Maxwell perceived, were not only between physical phenomena, but between different ways of thinking. He bridged experiment and theory, intuition and mathematics, visualization and abstraction. This integrative ability made his work resilient. Even when specific models were later abandoned, the core insights remained valid because they were rooted in deep structure rather than surface detail. Maxwell's approach also reshaped how scientific explanation itself was understood. Before him, explaining a phenomenon often meant describing how objects interacted. After him, explanation increasingly involved describing how fields behaved. This shift had profound consequences. It changed what scientists considered fundamental and what they considered derived. Objects became secondary to fields, interactions became processes rather than instant actions. This conceptual shift required a different kind of thinking, one that Maxwell embodied naturally. He was comfortable reasoning about continuous distributions rather than discrete points, about processes rather than events. This orientation allowed him to capture phenomena that unfolded over space and time, such as waves and propagation, with remarkable clarity. Maxwell's mind also operated with a strong sense of coherence across scales. He did not see a sharp divide between microscopic and microscopic phenomena. The same principles that governed small currents and magnets, he believed, should apply to large-scale processes like light traveling through space. This belief encouraged him to apply electrical and magnetic reasoning to optical phenomena, a move that would prove decisive. Despite the originality of his thinking, Maxwell was deeply respectful of empirical evidence. He did not dismiss experimental laws, he absorbed them. His genius lay in organizing them into a coherent whole. He treated experimental results as pieces of a larger puzzle, each one carrying partial information about an underlying structure. His task, as he saw it, was to reconstruct that structure. This reconstructive effort required both imagination and discipline. Maxwell had to decide which features of phenomena were essential and which were incidental. He had to distinguish between deep principles and surface effects. This discernment was one of his greatest strengths. It allowed him to simplify without oversimplifying, to unify without distorting. The invisibility of the connections Maxwell saw also meant that he often worked in intellectual isolation. Few of his peers fully understood his methods or conclusions. This isolation could have been discouraging, but Maxwell seemed largely unaffected by it. He was motivated by internal coherence rather than external approval. His satisfaction came from resolving conceptual tensions, not from winning arguments. Over time, the connections he revealed began to reshape physics. Others built upon his ideas, sometimes without fully appreciating their origin. The field concept became central to understanding forces. The notion that interactions propagate at finite speeds replaced instant action. The idea that light belongs to the same family as electrical and magnetic phenomena transformed optics and electromagnetism alike. All of this traces back to the unique qualities of Maxwell's mind. He saw unity where others saw division. He trusted abstract reasoning when guided by logic and symmetry. He was willing to work with invisible entities if they brought clarity. He valued coherence over convenience. These traits combined to create a way of thinking capable of revealing deep connections hidden beneath the surface of nature. The second keynote is therefore not just about Maxwell as an individual, but about a mode of thought. It shows how intellectual breakthroughs depend on the ability to integrate, to imagine, and to question assumptions. Maxwell's mind serves as an example of how science advances when curiosity is paired with rigor, and when imagination is disciplined rather than suppressed. In the end, the invisible connections Maxwell saw were always there. They did not come into existence because he discovered them. What changed was human awareness. Maxwell gave science a new lens through which to view reality, one that revealed harmony beneath apparent diversity. His mind acted as a conduit through which nature's hidden unity became visible. This legacy extends far beyond the specific theories he developed. It lives on in the way scientists think about problems, in the value placed on unification, and in the willingness to explore abstract ideas with confidence. Maxwell's genius reminds us that the greatest discoveries often begin as subtle shifts in perspective, moments when someone dares to see the world differently and follows that vision wherever it leads. At the heart of James Clerk Maxwell's legacy lies a set of equations so profound that they quietly reshaped humanity's understanding of reality. These equations did not merely describe electricity and magnetism, they revealed a new way of thinking about space, time, and motion. The third keynote, the equations that changed how reality is understood, is the story of how abstract symbols on paper became one of the most powerful lenses through which the universe is seen. Before Maxwell, equations in physics were often fragmented, each one tied to a specific experiment or limited situation. They described how forces acted between objects under carefully controlled conditions. Maxwell approached equations differently. To him, mathematics was not just a tool for calculation, it was a language capable of expressing deep physical truth. He believed that the right equations could uncover relationships that experiments alone could not yet reveal. Maxwell began by gathering the known experimental laws of electricity and magnetism. These laws worked well individually, but they lacked unity. Some described how electric charges exert forces. Others explained how currents produce magnetic effects. Still others captured how changing magnetic fields induce electric currents. Maxwell did not treat these laws as isolated facts. He treated them as clues, each pointing toward a more comprehensive framework. One of Maxwell's most important conceptual moves was to describe electric and magnetic phenomena in terms of fields. Instead of focusing on charges and currents alone, he described how electric and magnetic fields fill space. This shift allowed him to write equations that applied not just at specific points, but throughout entire regions of space. It transformed physics from a science of objects to a science of continuous processes. As Maxwell worked, he noticed something subtle but crucial. The existing equations describing magnetism seemed incomplete. They worked for steady currents, but they failed to account for situations where electric fields changed over time. Maxwell realized that nature would not allow such an imbalance. If changing magnetic fields could produce electric effects, then changing electric fields should produce magnetic effects as well. This symmetry was too compelling to ignore. To restore balance, Maxwell introduced an additional term into the equations governing magnetism. This term represented what he called a displacement current, a changing electric field that behaves like a current even in the absence of moving charges. At the time, this idea seemed abstract and unnecessary. No experiment had directly observed such a current, yet mathematically and conceptually, it completed the system. This single addition transformed the entire structure of electromagnetic theory. With it, the equations became symmetrical and self-consistent. Electric and magnetic fields were no longer separate actors. They became intertwined aspects of a single phenomenon, each capable of generating the other. The equations now described a dynamic system capable of sustaining oscillations. When Maxwell analyzed the consequences of his completed equations, he discovered something astonishing. They predicted the existence of waves that could travel through space without the need for charges or currents. These waves arose naturally from the interplay of electric and magnetic fields. A changing electric field would produce a changing magnetic field, which would in turn produce a changing electric field, and so on. The result was a self-propagating wave. Maxwell calculated the speed at which these waves would travel. He did this using known electrical and magnetic constants that had been measured independently in laboratories. When he performed the calculation, the result matched the known speed of light. This was not a coincidence, it was a revelation. Light itself was an electromagnetic wave. With this insight, Maxwell's equations transcended their original purpose. They were no longer just about electricity and magnetism. They explained the nature of light, uniting optics with electromagnetism in a single theoretical framework. A phenomenon that had been studied separately for centuries was suddenly revealed as part of a larger whole. The implications of this discovery were immense. Light was no longer a mysterious entity requiring its own special explanation. It became one example of a broader class of electromagnetic waves. Maxwell's equations predicted that other such waves should exist, with different wavelengths and frequencies. At the time, none of these waves had been observed. Yet the equations insisted they were real. This was a bold moment in the history of science. For perhaps the first time, a theory predicted entirely new phenomena before any experimental evidence existed. Maxwell trusted his equations enough to accept this conclusion. He did not claim certainty, but he recognized that the mathematical structure pointed clearly in this direction. Decades later, experiments would confirm the existence of radio waves, validating Maxwell's insight. Maxwell's equations also changed how scientists understood causality and time. Because electromagnetic effects propagated at a finite speed, changes in one place could not influence another instantaneously. This forced physicists to rethink the nature of interaction. Cause and effect became linked through the propagation of fields, rather than instantaneous action. Space and time became active participants in physical processes. The equations revealed that empty space could support energy and motion. This was a radical idea. Previously, energy was associated with matter and motion of objects. Maxwell showed that energy could exist in fields spread throughout space, moving even where no matter was present. This concept would later play a central role in the development of modern physics. Another revolutionary aspect of Maxwell's equations was their universality. They applied equally to laboratory experiments and to cosmic phenomena. The same equations that described a spark in a wire also described light from distant stars. This universality reinforced the idea that the universe operates according to consistent principles across all scales. Despite their power, Maxwell's equations were initially met with confusion and resistance. Many physicists found them too abstract, too mathematical, and too detached from experiment. Some struggled to interpret the physical meaning of the displacement current. Others questioned the reality of electromagnetic waves that had not yet been observed. Maxwell himself was aware of these difficulties and presented his work with caution. Over time, the equations were refined and simplified by later scientists. Their modern vector form differs from Maxwell's original presentation, but the underlying ideas remain the same. This refinement did not diminish Maxwell's contribution, it highlighted the depth of his insight. The fact that his ideas could be expressed more elegantly later is a testament to their foundational nature. Maxwell's equations also laid the groundwork for future revolutions. When scientists later discovered that the speed of light is the same for all observers, they encountered a conflict with classical ideas of space and time. Resolving this conflict would lead to Einstein's theory of relativity. Einstein himself acknowledged that Maxwell's equations were a primary inspiration for his work. In this sense, Maxwell's equations did more than explain existing phenomena. They reshaped the conceptual landscape of physics. They forced scientists to abandon comfortable assumptions and adopt a new worldview in which fields, waves, and finite propagation speeds played central roles. The equations also demonstrated the power of unification. By bringing together electricity, magnetism, and light, Maxwell showed that seemingly different phenomena could be understood through a single set of principles. This success encouraged physicists to search for further unifications, a quest that continues to this day. What makes Maxwell's equations truly extraordinary is that they are both simple and profound. Written compactly, they contain an immense amount of information. They describe how fields are generated, how they interact, and how they evolve. They encode the behavior of one of the fundamental forces of nature in a remarkably elegant form. For Maxwell, these equations were not an end in themselves. They were a means of understanding the structure of reality. He believed that mathematical beauty and physical truth were closely linked. His equations embodied this belief, revealing patterns and symmetries that suggested a deep order underlying the universe. The third keynote is therefore a story of how mathematics can reveal reality in ways that transcend direct observation. Maxwell's equations changed not only what scientists knew, but how they thought about knowing. They showed that abstract reasoning, guided by consistency and symmetry, could uncover truths hidden beyond the reach of immediate experiment. Through these equations, Maxwell gave humanity a new map of the physical world. This map did not replace observation, it organized it. It did not eliminate mystery, it clarified it, and in doing so, it transformed physics from a collection of separate rules into a coherent vision of how reality itself is structured. As the implications of Maxwell's equations slowly unfolded, their true power began to emerge in ways that even their creator could not fully anticipate. What had started as an effort to organize known electrical and magnetic laws became a profound redefinition of what physical explanation meant. Reality itself seemed to shift, no longer centered on solid objects acting instantly across empty space, but on continuous fields evolving through time. One of the most subtle yet revolutionary consequences of Maxwell's equations was the way they treated space. Space was no longer an inert stage on which physical events happened. It became an active medium capable of storing energy, transmitting motion, and shaping how forces behaved. Electric and magnetic fields could exist even in regions where no matter was present, carrying energy and momentum through what had once been considered nothingness. This idea challenged centuries of intuition and forced scientists to rethink the nature of existence itself. The equations also revealed a deep relationship between energy and geometry. Energy was no longer confined to moving particles or mechanical systems. It could be distributed across space in the form of fields, flowing and transforming according to precise mathematical rules. This realization blurred the boundary between matter and emptiness. Empty space, filled with electromagnetic fields, became something dynamic and physically meaningful. Maxwell's work also transformed the concept of waves. Before him, waves were associated with material media. Water waves required water, sound waves required air. Maxwell showed that waves could exist without a traditional medium, sustained instead by the mutual reinforcement of electric and magnetic fields. This was a conceptual leap that required letting go of familiar analogies. The wave no longer needed something to wave, the fields themselves were enough. This idea initially unsettled many physicists. How could waves travel through a vacuum? What exactly was oscillating? Maxwell's equations answered these questions in a new way. What oscillated was not matter, but the values of the fields themselves. Electric fields changed in time, creating magnetic fields, which in turn created electric fields, forming a self-sustaining pattern of motion. The wave was not something added to space, it was something space itself could do. The predictive power of the equations became one of their most convincing features. They did not merely account for known phenomena, they anticipated new ones. By allowing for a wide range of wave frequencies, Maxwell's theory implied the existence of electromagnetic radiation beyond visible light. This included waves with longer wavelengths and lower frequencies, as well as waves with shorter wavelengths and higher energies. At the time, none of these had been observed, but the equations insisted on their reality. When these predictions were eventually confirmed through experiment, Maxwell's equations gained an almost mythical status. They demonstrated that mathematics, when guided by physical insight, could see further than experimental instruments. This reversed the traditional relationship between theory and experiment. Theory was no longer just a summary of observations, it became a guide to discovery. The equations also introduced a new understanding of causality. Because electromagnetic influences propagate at a finite speed, events are connected through a chain of field interactions unfolding over time. This meant that the present state of a field depends on its past, and the future depends on how it evolves. Cause and effect became distributed processes rather than instantaneous actions. This shift had far-reaching philosophical implications, influencing how scientists thought about determinism and the flow of time. Another profound aspect of Maxwell's equations was their invariance. The form of the equations remained the same regardless of the specific situation to which they were applied. Whether describing a laboratory experiment or a cosmic phenomenon, the same mathematical structure applied. This universality suggested that the equations captured something fundamental about nature, something not tied to particular circumstances or scales. As physicists explored the consequences of this invariance, they encountered surprising tensions with classical ideas of motion and reference frames. The equations implied that the speed of electromagnetic waves was fixed, independent of the motion of the source or observer. This result conflicted with traditional notions of relative motion and would later play a crucial role in reshaping the concepts of space and time. Although Maxwell himself did not resolve these tensions, his equations made them unavoidable. They forced physicists to confront inconsistencies that had been hidden by earlier assumptions. In this way, Maxwell's work acted as a catalyst, driving the development of new theories that would redefine physics in the 20th century. The influence of the equations extended beyond theoretical physics into practical technology. Once electromagnetic waves were experimentally confirmed, engineers learned to generate, manipulate, and detect them. Communication technologies emerged that relied directly on the principles encoded in Maxwell's equations. Signals could be transmitted across vast distances without wires, carried by invisible waves predicted decades earlier. This practical success reinforced the credibility of Maxwell's theoretical vision. It demonstrated that deep, abstract understanding could lead to concrete applications with transformative impact. The equations became not only a foundation of physics, but a blueprint for modern civilization. From radio and television to radar and wireless networks, countless technologies trace their origins to the structure Maxwell revealed. Yet, despite their success, Maxwell's equations retained an air of mystery. They were compact, elegant, and deceptively simple, yet they described an astonishing range of phenomena. Physicists marveled at how much information could be packed into such a small mathematical space. This efficiency became a benchmark for what a successful physical theory should look like. The equations also influenced how scientists evaluated theories. Beauty, symmetry, and simplicity gained new importance. Maxwell's work suggested that these qualities were not merely aesthetic preferences, but indicators of deep truth. This idea would later inspire generations of physicists to seek elegant formulations of natural laws, trusting that simplicity often reflects fundamental structure. In teaching and learning physics, Maxwell's equations became a rite of passage. To understand them was to gain entry into a deeper level of comprehension. Students struggled with their abstraction, but those who mastered them discovered a powerful way of thinking about the world. The equations trained minds to reason about fields, waves, and continuous change rather than discrete objects and isolated events. Maxwell's equations also reshaped scientific language. Terms like field, wave, and propagation acquired precise meanings grounded in mathematics. This precision allowed scientists to communicate complex ideas with clarity and consistency. It also enabled collaboration across disciplines, as the same equations applied to problems in optics, electronics, and even astrophysics. Over time, the equations became so integrated into physics that it became difficult to imagine the field without them. They formed the backbone of classical electromagnetism and influenced the development of quantum theory and relativity. Even when later theories modified or extended Maxwell's framework, they did so by building upon it rather than replacing it entirely. The enduring relevance of Maxwell's equations speaks to their depth. They were not tailored to a narrow range of phenomena, but captured a fundamental aspect of how the universe operates. Their ability to remain useful across changing scientific paradigms is a testament to Maxwell's insight. At a philosophical level, the equations challenged humanity's understanding of what is real. They showed that reality includes not only tangible objects, but invisible structures governed by mathematical relationships. Fields, though unseen, became as real as matter. This broadened the concept of existence itself and expanded the scope of scientific inquiry. Maxwell's achievement also highlighted the creative dimension of science. His equations were not inevitable. They emerged from a particular way of thinking shaped by intuition, imagination, and aesthetic judgment. Another scientist, working with the same experimental data, might not have seen the same connections. Maxwell's work reminds us that scientific progress depends on human creativity as much as on empirical facts. In the end, the equations that changed how reality is understood did so quietly. They did not announce a revolution with spectacle or drama. They simply worked, revealing patterns that made sense of the world in a new way. Their impact grew gradually as their implications were explored and confirmed. Today, Maxwell's equations are taught as foundational truths, but it is worth remembering how radical they once were. They challenged assumptions about space, time, energy, and causality. They unified disparate phenomena and predicted new ones. They transformed mathematics into a window on reality. The third keynote, then, is not just about equations, but about a shift in worldview. Through a handful of mathematical statements, Maxwell showed that reality is more interconnected, more dynamic, and more elegant than previously imagined. He demonstrated that understanding the universe requires both precise calculation and bold imagination. By giving form to invisible processes, Maxwell's equations changed how humanity sees the world. They taught us that beneath the surface of everyday experience lies a structured, harmonious reality governed by deep principles. And in revealing that structure, they reshaped science itself, opening paths that continue to be explored more than a century later. The moment Maxwell realized that light itself was an electromagnetic phenomenon marked one of the most profound turning points in the history of science. What had once seemed like a familiar, almost ordinary aspect of daily life was suddenly revealed as a manifestation of deep and invisible forces. Light was no longer just illumination, it became a moving pattern of electric and magnetic fields, traveling through space with astonishing precision and consistency. For centuries, light had been treated as something special, set apart from other natural phenomena. It was studied through optics, lenses, reflection, and refraction. Astronomers relied on it to explore the heavens, and artists depended on it to shape beauty. Yet its true nature remained elusive. Theories competed, some describing light as streams of particles, others as waves moving through an unseen medium. None of these explanations connected light to electricity or magnetism in any meaningful way. Maxwell's equations changed this perspective completely. When he analyzed the mathematics describing electric and magnetic fields, he discovered that they allowed for self-propagating waves. These waves did not require wires, charges, or physical contact. They could move freely through space, sustained by the mutual interaction of electric and magnetic variations. When Maxwell calculated their speed and found it matched the known speed of light, the conclusion was unavoidable. Light was an electromagnetic wave. This insight unified entire branches of science. Optics, which had developed independently for centuries, became part of electromagnetism. Light was no longer an isolated mystery, but a member of a vast family of electromagnetic phenomena. Colors, reflection, refraction, and polarization could now be understood as consequences of electromagnetic behavior rather than separate optical rules. The idea that light is an electromagnetic wave also transformed how scientists understood the universe. Light from distant stars, traveling for millions of years across empty space, was now seen as energy carried by fields, rather than particles drifting through an ether. Space itself became an active participant, capable of supporting and transmitting these waves. The cosmos was no longer dark emptiness punctuated by light, but a dynamic arena filled with electromagnetic activity. This revelation also explained why light behaves the way it does, its constant speed, its ability to travel through vacuum, and its interaction with matter all followed naturally from Maxwell's theory. What had once required separate assumptions now emerged from a single coherent framework. The elegance of this explanation strengthened confidence in the idea that nature is governed by unified principles. Maxwell's insight went even further. If light was just one kind of electromagnetic wave, then other kinds must exist. Waves with longer wavelengths than visible light and waves with shorter wavelengths were implied by the equations. This was a bold prediction at a time when no such waves had been observed. Yet the logic was inescapable. Nature could not stop at the narrow range visible to human eyes. Later discoveries would confirm this vision. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays would all be revealed as different expressions of the same electromagnetic phenomenon. Maxwell's work thus expanded the human sensory horizon far beyond natural vision, opening vast new windows on reality. The unification of light with electricity and magnetism also had practical consequences. Understanding light as an electromagnetic wave laid the foundation for modern communication, imaging, and energy technologies. From radio transmission to fiber optic cables, from medical imaging to satellite navigation, the modern world is built on principles that trace directly back to Maxwell's insight. Perhaps most importantly, this discovery reshaped scientific thinking itself. It demonstrated that phenomena once thought fundamentally different could share a common origin. It encouraged physicists to search for deeper connections and to trust the unifying power of theory. Maxwell's identification of light as an electromagnetic wave became a model for future unifications in science. In revealing the true nature of light, Maxwell did more than solve a long-standing mystery. He showed that the universe speaks a single language, even when it appears to speak in many voices. Light, electricity, and magnetism were no longer separate stories, but chapters of the same narrative, a narrative that continues to shape human understanding of the cosmos. James Clerk Maxwell lived at a strange intersection of history, where revolutionary ideas could be born yet go largely unnoticed. Despite the depth and originality of his work, he never became a public figure in the way some of his scientific predecessors and successors did. He did not cultivate fame, and he did not seek to persuade the world through spectacle. His genius unfolded quietly, almost invisibly, and for much of his life, the true significance of his contributions remained unrecognized. Maxwell worked in an era that was not yet ready to fully understand him. His ideas were mathematically dense and conceptually radical, far removed from the experimental traditions that dominated physics at the time. Many of his contemporaries were skilled experimenters, but uncomfortable with abstraction. Maxwell's equations, filled with unfamiliar concepts like fields and displacement currents, seemed inaccessible and overly complex. As a result, his work circulated within a narrow academic circle rather than capturing widespread attention. Part of this quiet reception was due to Maxwell's personality. He was modest, introspective, and uninterested in self-promotion. He preferred teaching, thinking, and refining ideas to public debate or confrontation. Unlike figures who thrived on intellectual rivalry, Maxwell avoided controversy. He presented his work carefully and cautiously, often underplaying its implications. This restraint, while admirable, contributed to the slow recognition of his genius. Another factor was timing. Scientific revolutions often require both insight and readiness. Maxwell provided the insight, but the scientific community lacked the conceptual tools and experimental evidence needed to fully appreciate it. Electromagnetic waves, for example, had not yet been observed. Without direct experimental confirmation, many physicists viewed Maxwell's predictions as speculative. His work seemed elegant but unproven, impressive but distant from practical reality. Even within academic circles, Maxwell's ideas were sometimes misunderstood. Some reduced his work to a clever mathematical reformulation of existing laws, missing its deeper unifying significance. Others focused on specific technical details, while overlooking the broader conceptual shift he had introduced. The idea that light, electricity, and magnetism were fundamentally the same phenomenon was so radical that it took decades to be fully absorbed. Maxwell himself did little to correct these misunderstandings. He did not aggressively defend his ideas or insist on their importance. He trusted that clarity would emerge with time. This patience reflected his character, but also meant that recognition came slowly. He continued his work, teaching and researching, without knowing how profoundly he had changed the future of science. Tragically, Maxwell's life was cut short. He died in 1879 at the age of 48, before experimental confirmation of electromagnetic waves and before the technological revolution his work would enable. He did not live to see radio communication, wireless transmission, or the global impact of electromagnetic theory. Much of the credit for applying his ideas would go to later scientists and engineers. Only after his death did the true scale of Maxwell's contribution become widely recognized. When experiments confirmed the existence of electromagnetic waves, his equations gained new authority. As technologies based on electromagnetism transformed society, the foundational role of Maxwell's work became undeniable. Historians of science began to place him alongside Newton and Einstein as one of the great architects of physical understanding. This delayed recognition reveals an important truth about scientific progress. The value of an idea is not always immediately apparent. Revolutionary insights can be overlooked when they challenge prevailing assumptions or require new ways of thinking. Maxwell's story reminds us that genius does not always announce itself loudly. Sometimes it works quietly, waiting for the world to catch up. Maxwell's obscurity during his lifetime does not diminish his achievement, it enhances it. He worked not for applause, but for understanding. His motivation was internal, driven by curiosity and coherence rather than recognition. This purity of purpose allowed him to pursue ideas that others might have abandoned for lack of immediate reward. Today, Maxwell's name is inseparable from modern physics, yet his life remains a reminder that true influence is not always visible in the moment. His genius reshaped science from the inside, altering its structure rather than its surface. The world he helped create is so familiar now that it is easy to forget how radical his ideas once were. In reflecting on Maxwell's quiet genius, we are reminded that progress often depends on those who work patiently in obscurity. Their contributions may not be celebrated immediately, but they lay the foundations upon which future generations build. Maxwell connected forces, unified disciplines, and revealed hidden order, all without seeking recognition. His story challenges modern notions of success and fame. It shows that lasting impact does not require visibility or acclaim. It requires insight, integrity, and dedication to truth. Maxwell's genius, overlooked in his own time, continues to shape ours, proving that the most powerful ideas do not always arrive with fanfare, but with quiet certainty. The modern world runs on invisible forces that most people never stop to consider, yet nearly every one of them traces back to the ideas James Clerk Maxwell set in motion. His work did not remain confined to chalkboards and academic journals. It escaped into the world, shaping technologies that define everyday life. What makes this transformation remarkable is that Maxwell himself never designed a radio, built a power grid, or launched a satellite. He simply revealed how nature works, and that understanding became the foundation upon which modern technology was built. Once electricity and magnetism were understood as two aspects of the same phenomenon, engineers gained a powerful new toolkit. They were no longer experimenting blindly with wires and magnets. They could predict how currents would behave, how fields would spread, and how energy would flow. This shift from trial and error to theory-driven design accelerated technological progress at an unprecedented pace. One of the earliest impacts of Maxwell's work appeared in communication. His equations predicted electromagnetic waves that could travel through space without wires. When these waves were later generated and detected, the age of wireless communication began. Radio signals carried voices and information across vast distances, collapsing space in a way previously unimaginable. What had once required physical connections now required only an understanding of fields and frequencies. From radio came television, radar, and eventually the complex web of wireless technologies that surround us today. Mobile phones, Wi-Fi, Bluetooth, and satellite communication all operate by manipulating electromagnetic waves in precise ways. Every message sent through the air, every signal received from orbit, follows rules first written by Maxwell. His theory became the invisible infrastructure of global communication. Electric power systems also owe their existence to Maxwell's unification. Understanding how electric and magnetic fields interact made it possible to generate, transmit, and distribute electrical energy efficiently. Power plants, transformers, and transmission lines rely on electromagnetic principles to move energy across entire continents. The lighting of cities, the operation of factories, and the functioning of modern homes are all grounded in this understanding. Medical technology provides another striking example of Maxwell's legacy. Imaging techniques such as X-rays, MRI, and other electromagnetic-based methods allow doctors to see inside the human body without surgery. These tools depend on precise control of electromagnetic waves and fields. They save lives daily, applying abstract 19th-century theory to the most human of concerns: health and survival. Even computing and digital technology rest on Maxwell's foundations. Electronic circuits operate through controlled electric and magnetic interactions. Data storage, signal processing, and display technologies all rely on electromagnetic behavior. The screens that transmit information, the processors that compute it, and the networks that distribute it are all manifestations of Maxwell's insight. Perhaps the most far-reaching impact of Maxwell's work is how it changed engineering culture itself. Engineers gained confidence in theory as a guide to innovation. Instead of relying solely on experimentation, they could design systems based on mathematical principles, knowing that the behavior of fields would follow predictable laws. This marriage of theory and practice became a defining feature of modern engineering. Maxwell's influence also extended into energy transmission beyond Earth. Space exploration depends on electromagnetic communication. Signals sent to and from spacecraft, probes, and satellites rely on the same principles that describe light itself. Without Maxwell's equations, modern astronomy and space science would be unthinkable. What is remarkable is that all of this emerged from a single unifying insight. Maxwell did not invent specific devices, he revealed a universal framework. This framework proved flexible enough to support innovations he could never have imagined. It adapted to new materials, new scales, and new purposes without losing its validity. The technologies shaped by Maxwell's work have also transformed human society. They altered how people communicate, work, learn, and connect. Distance became less relevant. Information moved at the speed of light. Economies, cultures, and relationships were reshaped by the ability to transmit energy and data instantly across the globe. Maxwell's contribution reminds us that fundamental science often has the greatest long-term impact. At the time of his work, there was no clear path from abstract equations to practical machines. Yet by uncovering the structure of nature, Maxwell made entire industries possible. His legacy shows that understanding precedes application, and that deep knowledge can unlock possibilities far beyond immediate imagination. In the end, Maxwell made the modern world possible not by building it himself, but by revealing the rules that govern it. Every time a signal crosses the sky, a device powers on, or information flows invisibly through space, it echoes the insight of a quiet scientist who connected light, electricity, and magnetism into a single, enduring vision of reality. James Clerk Maxwell's greatest achievement was not confined to his lifetime, nor was it limited to a single discovery. His true legacy unfolded slowly, expanding across generations and reshaping science in ways that continue to this day. What he left behind was not just a theory, but a new way of understanding the universe, one that revealed deep unity beneath apparent diversity and set the direction for modern physics. After Maxwell's death, his ideas began to show their full power. When electromagnetic waves were experimentally confirmed, his equations moved from abstraction to undeniable reality. They became the foundation upon which entire fields of research were built. Scientists realized that Maxwell had not merely explained electricity and magnetism, he had uncovered a fundamental structure of nature that would guide inquiry far into the future. One of the most profound effects of Maxwell's work was its influence on how scientists think about physical laws. He demonstrated that the universe could be described through elegant, unified equations that apply universally. This inspired later physicists to search for similar unifications, believing that nature favors coherence and simplicity. The pursuit of unified theories, from relativity to quantum field theory, carries Maxwell's intellectual signature. Albert Einstein openly acknowledged this influence. Maxwell's equations posed deep questions about space and time that classical physics could not answer. The constancy of the speed of light, implied by Maxwell's theory, forced a radical rethinking of motion and simultaneity. Einstein's theory of relativity emerged directly from the need to reconcile these implications. Without Maxwell, relativity would not exist in its modern form. Maxwell's legacy also extends into the quantum world. As physicists explored the interaction between light and matter, they encountered phenomena that classical electromagnetism could not fully explain. This tension led to the development of quantum theory. Yet even within quantum mechanics, electromagnetic fields remain central. Quantum electrodynamics, one of the most successful theories in science, is a direct descendant of Maxwell's framework. Beyond physics, Maxwell's work influenced scientific methodology itself. It validated the power of theoretical insight to predict new phenomena. His equations showed that mathematics could uncover aspects of reality long before experiments confirmed them. This strengthened confidence in theory as a driving force of discovery, encouraging scientists to explore bold ideas guided by consistency and symmetry. Maxwell also changed how humanity views invisible forces. Before him, unseen phenomena were often treated with suspicion or reduced to mathematical tricks. After him, fields became accepted as real physical entities. This shift expanded the concept of reality and allowed science to engage with deeper layers of nature. It opened the door to understanding forces that cannot be directly observed but shape the universe profoundly. Culturally, Maxwell's legacy is woven into everyday life. The technologies that define modern civilization, communication networks, medical imaging, digital systems, and space exploration, all rest on principles he revealed, yet his influence goes beyond technology. It shapes how people think about connection, energy, and the structure of the world. The idea that everything is linked by underlying forces has become part of the modern worldview. Maxwell's story also offers a powerful lesson about the nature of progress. His work was not immediately celebrated, and much of its impact emerged only after his death. This reminds us that the value of an idea is not measured by immediate recognition. True breakthroughs often require time, patience, and the willingness to think beyond current understanding. In education, Maxwell's legacy endures through the training of new generations of scientists and engineers. Learning his equations is not just an academic exercise, it is an initiation into a way of thinking that emphasizes unity, structure, and depth. Students who engage with his work learn to see beyond surface phenomena and to search for fundamental principles. Perhaps the most enduring aspect of Maxwell's legacy is the sense of wonder it inspires. His work reveals a universe governed by harmony and order, where diverse phenomena emerge from common foundations. This vision continues to motivate scientific exploration, reminding humanity that the world is intelligible, and that its deepest truths can be uncovered through careful thought and imagination. Maxwell did not seek to reshape the world, yet he did so more thoroughly than most. His legacy is not a monument or a machine, but a framework of understanding that continues to evolve. It lives in the equations that guide research, the technologies that shape society, and the questions that drive scientific curiosity. In connecting light, electricity, and magnetism, Maxwell connected past and future, theory and application, imagination and reality. His work stands as a testament to the power of human intellect to reveal the hidden order of the universe. Long after his lifetime, that order continues to unfold, guided by the insights of a quiet genius whose influence has become inseparable from the fabric of modern science.